Yes.
Yeah. Good evening, everyone. So I welcome you all for the first session. The first session, the resource person we have is Dr. Muralidhara Anandamurthy. He is a part of JMP Global team and heads JMP Academic for India. He holds a BTech, MBA and PhD. He has finished his BTech from Bangalore University and both his MBA and PhD from Visvesvaraya Technological University. He has served more than 22 years in analytics and data science industry and worked for Genpact, Target, and Danske, holding various leadership positions. He is also a trainer in statistical data analysis, data science, and ML, and design of experiments, and has conducted workshops for premier institutions like Indian Institute of Science, IIMs, IIT, BIT, NITs, and other academic institutions. He has authored several case studies for teaching and also co-authored a book on machine learning for business analytics from Wiley International Publications. He continues to learn and share in statistical thinking for problem solving. We might have heard of the term one-man army. So that phrase one-man army completely shoots for Dr. Muralidhara Anandamurthy as he is the uh, one-man army for JMP Academic in India. Sir, we are pleased to have you. The session is yours.
Thank you so much, Professor. That was a generous introduction. Thank you. Yeah, I assume that you people can see my screen and then you can hear me properly. So I assume that that's fixed. Okay.
Yes.
Um, Thank you so much. So first of all, I sincerely thank the leadership team here who giving me an opportunity, SSN University, and especially the Department of Chemical Engineering for organizing this event and giving me an opportunity to share my learnings and thoughts. I also thank in advance all the participants for their quality time, especially on this beautiful Monday morning. I know you have to beat traffic and reach home or wherever you are. Sometimes you're taking that. So for next 90 minutes, okay. So here is my plan. So we have a hard stop at 8 o'clock, so 8 p.m. Indian time IST. So here's the plan for next 90 minutes. So I'll focus on kind of demystifying what is analytics, AI, and ML. I think this is everybody knows this. I just want to take this opportunity to reinforce my own learning and understanding, especially working with customers and then working with the institutions on from that note. At the same time, I just want to give a little more highlights on role of analytics, AI, ML in business. I think now that AI, ML is omnipresent, it's you can use anywhere and it's everywhere. That's what we've been seeing this kind of used for informed decision making, kind of data enabled decision making, and that is kind of 50% of the time which I'm going to spend, and next 50% are 50% of the time or 40 to 50% of the time I'll demonstrate using a tool called jump software. We'll take a case study in chemical engineering. We will apply analytics, we will apply machine learning, okay, and we'll try to see how it can be deployed also, so that you can see visibly how what was the problem, how machine learning helped or analytics helped in solving this problem, so that you can also uh, experience a tool like Jump. And just the good news is, I was just talking to the professor now, that it's a software from SAS and it is completely free for all the research scholars, supervisors, or students, and then professors, so that they can use it for both teaching and academic research. So I'll give you the information. You can connect with me. It's absolutely fully functional software, is completely free for all the academic institutions. So given that, and then we'll open up for Q&A. We'll have at least 5-10 minutes for question and answer. That's what my thought process. I hope that is fine, Rajesh sir. I think that's the plan I have.
Yes, yes. Please go ahead, sir.
So I think this is this one is kind of everybody is aware of this kind of a Venn diagram. Here's a Venn diagram which illustrates. Just want to have that relationship with analytics, machine learning, and AI. For me, everything is kind of, if you look at the broader circle of analytics, I just want to explain a little bit here. It's includes a little bit of descriptive and diagnostic techniques, partially overlapping with machine learning. You can see that. Uh, for data and for predictions, kind of most a tool within analytics. I can say always from that perspective. So Analytics overlaps with ML and AI, broadly focused on deriving insights from the data. So it mostly focuses on understanding and visualizing the data. I can call analytics a little more exploratory data analysis. That's where it starts. And it focuses on understanding is the key. So most of the times, whenever we build any kind of statistical model or AI, we will have two important goals or objectives. One is to predict or to understand, and both of them are different. Okay, I know that if you understand well, you can predict better, but not in every use cases. From an industry perspective, you want to understand, especially from a retail or a banking, from a HR perspective, you don't need to understand too much. You just focus on the prediction perspective. So analytics helps you to understand a little better. And the second component is the machine learning. It's a smaller circle, if you see that within that, a little bit of smaller circle, but expanding into AI. Okay, I can call it a subset of analytics for me. That's how I've been seeing from last 25 years. It's a subset of analytics and AI. It mostly focuses on learning from data for predictions. Okay, within analytics and AI to create predictive models. Most of the times you apply machine learning to either predict a behavior or a phenomena, or else a classification, whatever. So that's where machine learning comes into the picture. The larger circle is the AI. Okay, so now from last few years, the way we've been seeing is it encompasses ML, the kind of analytics driven decision making. It also includes some of the non-machine learning technologies like rule-based systems sometimes. Okay, so it's a larger category. I would say it encompasses ML and other intelligent systems. Okay, you can consider AI as a overarching field, aiming for human-like intelligence, and it is powered by ML and advanced analytics. So AI has a backup powered by ML and analytics, one component I can say. So there are a lot of overlaps, but one thing has remained same from last 25 plus years, the way we've been seeing from an industry perspective is, I can use this word, okay, called statistical thinking. Okay, whatever we are talking about, AI, ML, deep learning, augmented intelligence, we're going to talk about that, or else your double deep learning. Now people have started using those kind of technologies and terminologies. But what has remained from a problem solving or engineering problem solving perspective is the statistical thinking. Okay, all these can be termed under one big umbrella called statistical thinking. What it talks about is any process, irrespective of industry, whether it's a chemical, manufacturing, services, agriculture, social sciences, all the processes have some variations. Okay, as an engineer or a scientist or a leader, as a manager, it's our goal to measure the variation in the process. Okay, and then understand, very important, the first is a measurement, and understand the variation, and thereafter try to reduce the variation. Understand includes prediction sometimes. So measure, understand, and reduce the variations. Sometimes you want to completely remove it. Not every time it is possible. We'll try to reduce the variation. That's how we take step by step kind of Kaizen approach towards that, whether it's manufacturing, service, or agriculture. That's what you apply those statistical techniques. You can call it as analytics, predictive modeling, data science, machine learning, AI. Okay, you can use synthetic data or a generative AI, whatever you're going to apply. The objective is to measure the variation, understand the variation, and reduce the variation in a process, whichever process industry you might be working in. This is what we define as statistical thinking. At the same time, if you look at from an engineering perspective, not everybody is into hardcore mathematics or statistics at the end of the day. From an application standpoint. Okay, so what we use in industry is we use softwares which can help us to perform the statistical data analysis, where you're applying any kind of machine learning algorithm or automation, those kind of. So it's more of applied problem solving using a technology, I can call it. This is where it fits in. Okay, with that background, some of the terminologies you might hear when we speak about AI/ML. Okay, so there are all these things have similar characteristics in one or the other way. The first similar character of analytics, AI, ML, whatever we are calling it as, all of them are data-centric approach. All these three heavily rely on data as the foundation for insights, decisions, and predictions. So it's a data-enabled decision making. Okay, so we always use the word D to D as a journey. Okay, data to decision as a journey. You have data, and there is a reason why you collected data. You're trying to solve a problem in industry, or else trying to capitalize on an opportunity. So for that reason, you collect data, and then you convert the data into information. And then once you convert that information, you add little more your experience and then subject matter expertise, and then it becomes insight. Okay, and then with that insight you apply context to it, and then based on the level of risk you have as an organization, or as a manager, as an individual capacity, or as a scientist, you take decision. So it's the flow from data, insights, okay, data, information, insights, and decision. We call it as D to D as a journey. That's what AIML is helping us to move from data to decision. All these applications or technologies will help to move the information and insights closer to the decision maker. End of the day, we want to take more efficient and effective decisions, and these are helping us to make better decisions. We call it as informed decision making. Analytics helps in making informed decision making, or AML. So then comes goal of insight and automation. And next extension is, once you want to make a decision, you took a decision, and most of the times you don't want to make repetitive decision. If it is standard, you can make a standard operating procedure or a protocol, so that not only they aim to enhance decision making and problem solving, often by automating the processes or by identifying the patterns in the data. And that's the next level. Okay, slowly moving ahead with automation and insight generation. And the most important thing is techniques like predictive modeling, okay, statistical data analysis, design of experiment, okay, simulation, optimization, clustering, okay, agent-based decision making. All these things are overlapping most of the times when it comes to your problem solving. So whenever you see a problem in industry, it depends on how much time you have, what kind of problem it is. Accordingly, you apply a specific tool or technique to solve that problem, and most of the times a combination of techniques or tools to solve the problem. The focus is on problem solving, and most of these techniques, there's nothing called earmarking, this is analytics, this is AI, this is ML, but most of the times from a problem solving perspective, all these things are overlapping. Okay, and the best part is they're iterative. It is not like that I fix a solution, fit a model to this, and then I'm done with it. No, this is iterative process. Okay, so refining the models or analysis based on the feedback, error, okay, data, new data coming in. So we always say, just like money has a time value, data also has a time value. We always look at the reliability, validity, all those. From a big data perspective, we have a little more velocity of the data, volume, variety, veracity. So given this context, it is not a one-time solution. It's an iterative process. It's a continuous process where you build a model, you build an AI application, and you see how it is performing. Okay, take the feedback and then refine your solution. So it's a continuous process, any kind of solution. And most importantly, this is interdisciplinary. Okay, now when I say interdisciplinary, they draw from fields, or the inputs from fields like statistics, computer science, mathematics, electrical engineering, okay, social sciences. It takes inputs from various fields, for example, healthcare, okay, finance. So it depends on which domain at the same time. And most of the times when we talk about AI and ML, there is one is a data component, another is a technique component, another one is a business component. There are three components which evolve or revolve around this. So equally important. Data is all your structured, unstructured data, image data, video, audio, and then comes all your techniques, statistical techniques. Sometimes you use programming languages like Python, C, Java, or else R. It's up to how do you want to convert the data to information? You can apply coding language or a no code software just to convert. And then once you have some kind of information, you have to have the business context. That is where I always say that AI cannot replace human beings, because end of the day, humans have to take the decision, and that they're really good at in subject matter. So you apply your subject matter knowledge to take final decisions. These are the common things across when we talk about AI ML. Level at which you're going to use might be different, but these are all common similarities across AI, ML, or data science or analytics, whatever we call it as. Then comes little more from I'm looking from aspects just to differentiate between analytics from a maturity standpoint. I think from a readiness perspective, even from a research or adoption in a commercial organization, uh, it has to go through some levels. After that, only you can deploy a fully functional AI solution, keeping your customers in focus. Okay, so the first one is I always look at the definition. If you look at these three analytics, machine learning, and as well as AI. So I just looked at the relative importance and complexity. Just to give you a ballpark green number, I'll start with analytics and then ML and then AI. If you look at from a definition standpoint, so analytics can be systematic analysis of data to derive insights and make decision. Uh, I would call ML as little more subset of AI focused on algorithms that learn from the data. The AI is a broader field of creating systems that kind of simulate human intelligence. We are trying to combine both innate intelligence and from a human perspective. That's what we are trying to build that intelligence into the machines. Then comes your focus. Okay, mostly analytics focuses on what happened and why, kind of. So, and then your machine learning helps you to predict or classify based on your learned patterns. Okay, and then little more AI focuses on the automating those tasks that requires little more reasoning and decision making from an intelligence perspective. You can see that from a scale. This is purely personal perspective, given the kind of exposure I have working with multiple industries. From a complexity perspective, okay, analytics is a little simpler. Okay, simple technique like descriptive statistics, analytics, or so inferential statistics, or a little more t-test, ANOVA, and a bit of multivariate to apply. You visualize the data, those kind of things you do with analytics. With a little bit of ML, you involves coding sometimes. You have to fine tune your algorithms. You might use a programming language, or there are other tools like Jump, which can help you not to code and then directly get into applying, deploying the ML algorithms. And from a AI perspective, automating that now that little more high complexity, because when you automate, you want to integrate multiple techniques and methodology and connect those data pipelines, and also you want to build that solutions, little more complexity. Okay, relatively. Then comes the scope. When you talk about scope, I think analytics is a little more broader in scope. Okay, so the way I look at it, covering descriptive, diagnostic, predictive, prescriptive, all those things from an analytics. The ML is a little more narrower. Okay, it's more of data-driven learning from a scope perspective. And AI is the broadest, according to me. It includes machine learning, robotics, natural language processing, all those things from a scope perspective. Then comes your tools and techniques. I think this is where highly subjective it is. You build dashboards, you build data visualization, apply statistical methods when it comes to analytics. And then you apply for ML, you apply algorithms like neural network, decision trees, or a little more generalized regression, or k-nearest neighbors, those kind of naive-based, those kind of clustering, those kind of algorithms when it comes to machine learning. AI, you combine both ML and NLP, little bit of computer vision, okay, robotics, okay, automated decision-making systems, those kind of when it comes to tools and methods for AI, okay. Just last is last, I think, human involvement. I think from an analytics perspective, a lot of human involvement is there. Just you want to explore the data, interpret the results, all those things. ML, little bit medium, I rate it as, which relies on kind of data scientists for training the models. Okay. And AI is little low human involvement. That's what is positioned as well, because it is designed to operate autonomously after development. Once you develop and deploy it, I think it requires little more feedback and maintenance, but from an involvement on a day-to-day perspective, it is less. That's what I position it as. Applications, just from a just general applications perspective, not from an industry, I'm looking at it. You can apply business intelligence, your typical trend analysis, kind of do dashboarding. That's where analytics fit into. And just an example is spam filtering out or product recommendations or your predictive maintenance. If you're trying to find out what are the reasons for a dissolution failure in a pharmaceutical sciences or a yield, why it is low in a manufacturing sector, probably you build a little bit of analytics followed by a machine learning algorithm to fine tune it. Or else when it comes to AI, it's more of a self-driving cars, your bots, virtual assistants. From an AI perspective, AI-powered drug discovery, those kind of applications. Just trying to give a perspective. And from an adoption perspective, it always goes how your data readiness, how much data is there, what is the kind of problem. Okay, at the same time, because we know AI, it doesn't mean that every problem needs to be addressed from an AI perspective. Look from a problem perspective, and then how much time, how much customer requirement, how much data readiness we have as an organization or from a research perspective, and then deploy. So I always remember my professor telling, if you want to hit a nail, especially from mechanical engineering, so if you want to hit a nail, you don't need to use a advanced Bosch kind of a drill kit. You just need a simple hammer. So we always say that it's not about the tool or the technology what you have. Look from a problem perspective. So that's more important. What is the problem? How can I solve this problem from data? Is there any question? Good to go? Okay. So I think you all know this. I think everywhere it's omnipresent. I use this word. I think you can use analytics or data science or machine learning or AI everywhere, irrespective of whichever domain you're working, agriculture, manufacturing, retail, media, government, okay, banking, pharma. And within those industries, you might have a lot of departments, kind of, as I said, that it's not only cross-functional, it's also cross-discipline, okay, interdiscipline and cross-functional, we always say that. So that's how AI, ML and analytics is positioned. It's more of a problem-solving tool than anything at this point of time. I think the more data-enabled decision-making is happening in the organization, that means they're trying to use data to make informed decisions rather than going on traditional gut feel-based decision making or rather any other illogical decision making. So that's where we are. I don't want to give you too much of use cases on this. I think you have seen many things on AI ML, how organizations are using, be it on a small operational level or at a mid strategic level or at the highest strategic level. Okay, you want to make a tactical decision, you can use AI ML. Or else at a little more mid-managerial or an engineer level that you can use. At the same time, highest strategic decisions can also be made using data, applying different tools and techniques. Something you watch. Okay, we are already. So we have 30, 20, 25 minutes before I get onto the actual demonstration or taking case studies. Just to give you perspective, analytics, we mostly look into three domains. Okay, what is descriptive, okay, and then predictive. Sometimes people use another word called diagnostic analytics also, but it's for me descriptive. It sits in between actually descriptive and predictive. Some people use diagnostic analytics. So majorly, if you look at the descriptive analytics, predictive analytics, and prescriptive analytics. Descriptive analytics is little more summarizing the data, kind of historical data you have, example, creating a reports or dashboards, what happened, okay? You're trying to answer a question, what happened? And then from a predictive, you start questioning how to forecast the future trends based on historical data. So what could happen? So you build models and then use techniques to forecast and understand or kind of predict future. Then comes the prescriptive. I think based on the historical data, you try to apply optimization algorithms, okay, kind of recommending the actions to optimize your outcome. So in most of the times you want to maximize your yield. Retrospectively, you would have collected some data, you build a predictive modeling and then optimize. Sometimes you have multi-response optimization is the word we use it. When you have multiple Y values, you apply algorithms like gradient descent or those kind of algorithms to optimize your process. The most important thing is what happened, what could happen, what you should do. I think these are the three questions analytics answers most of the times. Just to give an example, analyzing the sales data to identify the best selling drugs in a pharma company or a best chemical component in a chemical manufacturing sector. So those kind of analytics you can do, or why there is a low yield of a process. We'll take one chemical process example. We'll try to understand that as part of demonstration. Then comes a bit of AI. I normally take ML first and then, because now I see ML and AI, there's a lot of integration. And that's the reason I thought of choosing AI first. So if you look from a AI perspective, the definition normally, if you look at any of those, the leaders of AI being the SAS and IBMs of the world, it refers to a systematic computational analysis of data by combining kind of both innate intelligence and human ingenuity. Okay, so human beings have innate intelligence, which is defined as, for example, let's see, innate intelligence that governs every activity in our body. Okay, it's kind of which causes a mango tree to grow out of little seed. That is innate intelligence. Every living organism will have this. Single-celled organism to an elephant or a human being. That's called innate intelligence. Now, ingenuity is something, a skill at working out how to achieve things. Okay, for example, human ingenuity means human minds have influenced how we think, how we work, how we play, how we conduct friendships, how we interact with each other, how we create problems. That's important. Okay, how we solve our problems, how we create problems. That's all part of skill component. There's a governance component. There's a skill component. Okay, so HI includes, especially human ingenuity includes how human beings read, write, okay, and listen and do math, and then always comprehension also. This is the main skill set a humans have apart from innate intelligence. Now, this is what we are talking about. Seeing, hearing, speaking, writing, or say feeling and thinking. This is for your human ingenuity. So now this is where recognition and comprehension happens. Now slowly moving from that, now I'm moving or else I'm transferring this human intelligence or innate intelligence plus human ingenuity. I call it as human intelligence sometimes, by to a machine. Okay, how I'm going to transfer is through supervised learning, unsupervised learning, or reinforcement learning, and then so that machines can read and write and math little more intelligently. This is the ultimate objective of an AI tool. Okay, so you're trying to transfer your human innate intelligence and human ingenuity through some of the algorithms or some of the techniques like supervised learning, unsupervised learning, or reinforcement learning. Okay, so that machines can support us better. When I say machines, it includes both hardware and as well as software. How do we transfer? Learning. That's how machines are going to learn from us. So AI can do a little more reading, writing, comprehension, math, little more intelligence. Now, the most important thing is when we talk about AI, we are moving from points of data to point of view. That is where we are talking about the granularity. Okay, the data can be numbers, characters, audio, video, text, vectors. We call diverse big data. Okay, so AI enables, from an engineering standpoint, data points of data to point of view. We call it as, earlier we said that data to decision, that's their analytics. Now look at this, AI is point of data to point of view. So you've got little more additional value out of AI systems. Now, if you look at this from a definition standpoint, I've been using AI for a while. Most of us are familiar with the acronym called artificial intelligence, but somehow I stay away from using the word, the acronym. Okay, So AI for me is augmented intelligence. This is where, from a different perspective, this is okay. So AI is for me is augmented intelligence, which helps human experts to make evidence-based or so-called data-based informed decisions while machines do the time-consuming work. We are looking at cooperative environment. We are not looking at a competitive environment. Okay. We are looking at a cooperative environment where man and machine work seamlessly. Okay. So anything that makes machines act more intelligently is AI for us. Okay. AI should not attempt to replace human being. Everybody knows that. It should extend the human capabilities so that the task can be accomplished where for human beings is difficult, neither human beings nor machines can accomplish, but in combination we can accomplish. That's what we're talking about. Okay, so we have with the exploration, okay, what the kind of data what we have, the information, the faster distributed computing, the IoTs, we have massive amounts of data. I don't think so humans have time and then the kind of computational power to compute that. That's where we have started using machines. Okay, we want expert to scale their capabilities and let the machines do the time consuming work. So we define AI as augmentation to your augmentation to humanity or augmentation to human intelligence, not artificial. I know that people use that, but I normally stay away from defining AI as artificial. Instead of I use it augmented intelligence. Now what we're talking is scaling up human capabilities, advance information to decision makers, and synergize task accomplishment. These are the main three reasons why AI should be used in an organization. Okay, what I'll be talking is a 16 trillion USD industry now. So that's the expected addition to GDP by 2030. That means 16 trillion GSD addition. Okay, it's not exactly that much. So it's a enhancement to the existing GDP. What we're talking is, so that's predicted by PwC. Okay, so by 2030. So that means AI is everywhere. We are not looking at one domain here, and most of the times it's the I always call it as the circuital branch will complement the non-circuital branch. So people write code or develop technologies and solutions so that the non-circuital branch can perform really well. That's how we position. So from an AI perspective, that's where the three levels we talk about it. Okay, so weaker AI or a strong AI, or else it's a little more super AI. Oh, look at this. Weaker AI does little more specific task. Okay, we also call it as narrow AI. So just kind of a goal-oriented decisions like your Siri, okay, Alexa, are kind of weaker AI or narrow AI. Little more stronger AI is where your AI can solve unfamiliar problems. Okay, it's kind of general capability or machine intelligence. Okay, it starts replicating human intelligence. That's where strong AI comes into the picture. The next level AI is little more super AI. We also call it as conscious AI, where exactly human level consciousness is what we are trying to build. Somewhere we are migrating from narrow AI to strong AI. I think super AI is something which we want to be there. That's the aspirational AI, given that it's going to take a lot of time. Okay, so how these will be enabled from a AI ML or analytics perspective, I think from an enabler standpoint, you have GPUs now that they're key to AI. They provide heavy computational power because you need a lot of iterative processing and tuning your neural networks. Okay, your NVIDIA, AMD, Intel, that's where all the GPUs are coming from. And then the IoT component. Okay, you have massive amounts of data coming from connected devices. Most of it is unanalyzed, automating the models with AI. Kind of that's where the IoT position is. The most important things where most of the data engineers focus is building those portable packages of code. Okay, that's API that make it possible to add AI or ML functionality to the products and processes. And that's where you build software packages. Okay, they can add image recognition capabilities to home security systems or Q&A capabilities to describe data from a bot perspective. Okay, those kind of APIs you want to build. Okay, so again, The AI will always look at providing solutions. When you say solution, sometimes it is a software that can reason on an input and explain an output. That's what we're talking about from it. So you might have machine learning, deep learning, natural language processing, okay, or else computer vision. Those kind of all these capabilities are used. Okay, so ML, most of the times you have unsupervised learning. Okay, most of the where you have to have a target label and then create a predictive tool and then use that tool to apply it on a new data and then find out. It's kind of supervised learning. You might have unsupervised learning as well. Okay, where clustering is principal components. These are the different techniques for unsupervised learning. Then comes your semi-supervised learning and then reinforcement learning, little more on the agent-based decision making. Okay, so often reinforcement learning is used in robotics, gaming, and navigation. Okay, where the algorithm discovers through trial and error which actions yield the greatest reward. That's how it learns the environment, and then it's a kind of reward-based learning, agent-based learning. So as I told in the beginning, a lot of jargons in the beginning. I don't want to get into that more, but we'll take a simple case study as I mentioned. Okay, so we have a lot of deep learning algorithms. Okay, just to give you some of these things you would have learned. Some of you might be using in your research and teaching. Okay, all this whether speech to text, your CNNs, RNNs, GANs. Okay. DQNs, okay, deep reinforcement learning like deep Q networks or else um, variational auto encoders or else REST nets, DBNs, all those things you might be using. End of the day, they're trying to capture the patterns in data, trying based on that, they're trying to give you some decisions. You have transformers like BERT or GPT-3, okay, on those kind of stuffs. At the same time, we have a lot of so-called unstructured data, okay. Also, we call it as how can you extract information from your natural languages? That's also we are talking about it. Okay. So given that you're familiar with these, some of you are using this, some of these popular frameworks of deep learning also, be it PyTorch or TensorFlow or Keras. Some of you might use captive tools, some of you might use open source tools. End of the day, all of them are kind of talking and helping you to make better decisions within your own domain. Okay, so keep that in mind. To sum it up the theoretical component, what I had, we are trying to drive decisions based out of data and then moving data closer to the decision maker and trying to build some intelligence and then keeping the problem at the center. Okay, so very important, I always say, is your problem decides the program, not the program which decides the problem. So given that context, all this AI, ML, analytics solutions are built around the data, which is in turn connected with your problem. So there's always a problem from a research perspective, and then you collect data, or so-called from a PhD research perspective, or academic research. You have a research question and a research objective, and then to achieve that objective, you ask specific questions, and then to answer those specific questions, you put a research design and then create some questions out there, and then try to collect the data. And each of these data set is trying to answer a research question, which in turn supports your research objective. So it's always data is at the center, and then again data is collected based on your problem or an opportunity you're trying to solve. So this is one maximum theory I thought of putting across when you talk about AI ML. I will take one case study now that majority might be from engineering background. I didn't want to take a management background. Any questions till now? I assume that you're able to hear me and then see me, okay? Or watch my screen. Yes or no?
Yeah, there is a question one in the chat box asked by
Chat box.
Ashwin Mascarenas. Yeah, he is
Okay.
stating that
Chat box.
A
Okay.
is, yeah,
Yeah.
you can see it, right?
Oh yeah, A is the next stage of using ML engine, right? What are the additional things required to convert ML to AI, and what makes them? Again, so this is a good question. Okay, so now applying AI means the way I defined. If you remember this, okay. Now we are looking at AI for us as augmentation. Okay, so now anything which you use, given this context. I probably this one would be the better way to represent. Okay, I'll go back to this. This one. Okay, so there is always interconnections and overlapping. There is nothing called, you can't say that this is the Venn diagram, right? So you can't say this is what discriminates here. This to this is analytics, this to this is ML, this to this is AI. Okay, based on the problem, even if I'm putting a simple recommendation system, I can consider as an analytical solution or a machine learning solution or an AI solution. Okay, so AI is, as long as you are looking from a complexity and human involvement, if you're minimizing, probably that can be looking at automating and then kind of putting that on a self-drive mode. Okay, minimizing human intervention from a problem solving perspective, that could be an AI. Okay, at the same time, it depends on the complexity of problem. Now, for a simple manufacturing process, a quality is where I'll put a AI solution to measure quality. At the same time, if I'm looking from a drug discovery, the AI solution is a different one. You use many large language models in the back end and try to collect the data and then try to predict. Okay, or else simulate with little more synthetic data and then predict. That becomes an AI solution. So my focus of the way we define from an industry perspective is AI is something, as long as it augments the human decision making, probably that becomes an AI. For me, it's so difficult to discriminate what stops at ML or what stops at AI. Okay, so it's all, I would say, interconnected, and then there's overlapping. I'm sorry, I could not answer the question in a way you might anticipate, but this is what we believe. Okay, thank you so much. Great question. Any thoughts? Any other questions before I take a couple of case studies, and I'll try to apply analytics at the same time. I'll apply machine learning algorithm, and we'll try to create a code for deployment also. Okay, that's what the entire journey will go through from data to decision. Again, it is not about the program. It is not about the capability. It's not about the skill set. We always look at what is the problem. Okay, it's always problem-centric approach, data-enabled decision making. I always call it as from that perspective. Okay, good to go. Okay, let me increase this. There you go. Okay, should I go? Any other questions? Okay, so let's take, this is an example. I'm using a tool called JUMP, which is statistical discovery from SAS. Okay, so now this tool is completely free for all of you. I assume that many of you from academics. Okay, if you're from academic background, if you're a student or a research scholar or a professor, and this tool is completely free, you can download it. Okay, jump.com/student if you go, free for academic use. Don't worry, because it is academic use, we are not giving you a toned down version. It is a fully functional software which you can use it. Okay, for your teaching and as well as researchers, and it is made completely free for all the students, research scholars, and professors of educational institutions. I'm going to use this. It's a desktop-based tool, essentially a drag and drop tool. Okay, but at the same time, it is extensible with your open source like Python. Okay. Python or any kind of open source tool. Okay, so I'm just typing gem.com/student if anybody wants to follow it. If you want to follow along, this is the tool which I'm going to use it. It's a desktop-based tool. I'm not going to write any programs given the time constraints, but I'm going to use the drag and drop capability to simply solve this problem. Okay, yield of a chemical process is a challenge here. Look at this. Now, company sees that there's a 90 batches where they wanted to have a minimum of 70 as a yield, but they feel that there is a problem with the yield, and these are all the data retrospectively they have collected. Okay, so and they wanted to analyze. The problem is they wanted to understand. First thing is, okay, they want to understand what are the reasons for the lower yield. Okay, they wanted an average yield of 70-75. Now that the chemical process. Now, this is a data which is retrospectively collected, and then you can have the data in data warehouses or any format. You can import it, you can connect to data warehouses, and then it comes to the JUMP environment. This is like an Excel kind of a feel, you can see that. So given this, my goal is to find out what are the reasons for lower yield, and then I want to build a model to identify what are the main reasons, or is to establish a relationship between the variables which is causing lower yield, and then other variables. And then that's a simple analytical approach. At the same time, I can go ahead and build a little more advanced machine learning algorithm. And then I want to optimize also, kind of applying the machine learning algorithm, and then getting onto the optimization level. What should be my optimal factors, or so-called the input variables, which can maximize my yield? So I'm taking you through the decision by applying analytics and machine learning. And we also want to deploy it in the front end. That means I want a Python deployment code so as to complete the cycle. Okay. So we'll try to do that using, and I might, if time permits, I'll take another case study on mass, okay, material science kind of a case study using image data. How can you classify, provided that we get some time. But you can always follow on and download the software and use it. Okay. Now this is a data set. You can see yield, and then the best part is whenever somebody gives me a problem like this, okay, the first thing is somebody gives me data, the data won't be in this clean format most of the times. Okay, you might have a lot of outliers, missing values, and then you might have to clean the data set and then transformations, do all those. So I call it as jumbo circus, or cleaning the data, ensuring the data is ready for the analysis. I know most of you will take a lot of time, and including myself, getting the data in right shape so that I can start building the models and applying statistical methods to it. So now in this case, I've cleaned the data. Okay. So, but analyze many have many screening, exploring for outliers, missing values, patterns, and then you can do many things before getting the data in a clean format. Now that the best part is, especially from a consulting world, if somebody gives me a data that there is a problem, you need to fix it. First thing, I'll check whether the problem really exists. This is most important for me. So I'll just go, somebody says that yield is a problem. I just go from as a chemical engineer, I will just put a control chart and say I'll check for the yield here. Okay, so now I'll see that I'll see shaded zones here, and I can see I can put a lower control limit as 70 I want. So I can see, oh, there are a lot of batches which are lower than 70. Okay, lower than 70, I can see that, or lower than 75, I can set it up. Okay, so I can see that there are a lot of challenges here. I can also see a little more capability perspective. Okay, so I can check, let me check whether is there a real difference or not. I can go and then check a distribution of your yield. Okay, I'll check every distribution actually when I do any kind of building ML model, and I'll say, let me check continuous fit all, and then let's see which distribution fits better. Okay, so I can also put a little bit of process capability if I want to do a lower specification of 75. Let me put this here, 75 instead of 70. I want a little more higher. I can see this. Okay, I can see there are many batches which are less than 75. I want to improve or move the yield. Okay, so I want to find out. That means I just want to ensure that, okay, my problem really exists before I solve. Okay, that's very important. I think the reason why I'm telling you this with my personal experience, most of the times by the time we solve problem using data, somebody else would have already solved it, or else there's a time value of information. I always ensure the data, from the data perspective, the problem exists. Assuming that there is a yield issue with this process, I'll try to apply analytics first. That means I start visualizing the data. Okay, explore the data visually as part of analytics. I'll go and build. I use there are a lot of conventional graphing capabilities. I'll use graph builder. Well, I'll see. I can see. I'll put a histogram and see how majority of the yield is bit below. I can see 7 to 75, and I just look at this how it is split across agitation. I can see that agitation. If higher agitation have lower yield, I can also see a little bit of mean here. Okay, I'll put a label here, just using this. Okay, you can see that higher agitation is leading to lower yield. Okay, lower agitation is leading to higher yield. So that means there is some kind of relationship. I'm just exploring visually. You can also do that yield versus, I can select this and then modifier. Okay, I can see, is there any relationship? I can put a regression graph here. I can see with respect to time, is there any relationship? Looks like it's also directly proportional. Let me put this temperature. Temperature is an inverse relationship. I want to split this based on compressor. Okay, you can see that the relationship. This is a graphical way of exploring. You can build a dashboard using any of your capabilities. Now start exploring. You want to see the contour graph. So drag and drop, create your own graph, or else you want to create a heat map to see multiple variables. I'll take these variables, put it here. I want to see based on the heat map. It's kind of multi-dimensional capability. Start exploring the data and then unearth the insights from the data. That's what I'm trying to learn here. Or else I can go and put a little more three-dimensional graph between modifier, temperature, and time. And I'll put a three-dimensional graph and see how my yield is positioned from a 3D perspective. Looks like you can easily see that the lower temperature has higher yield. Okay, so I can see that from a combination of modifier and time. Little bit of exploring data visually. That's part of analytics for me. Or else you want to check which distribution it fits into. I can also do visually a little bit of checking every other distribution. I want to see histogram only. Okay, just to see that. I'll stack into kind of, no, I'll not stack it. I'll put it here, arrange into row of 6. Okay. So this is where your visual Six Sigma or else analytics comes into the picture. If I select less than 70 here on my distribution, see, everything related to lesser yield gets highlighted. You can see that this exactly we spoke. Look at this. Lower yield is related to higher agitation. I can visually see also. The same time, lower yield is related to lower time. Without building any model, I'm trying to understand from the data. Remember that we said that predictive models will help you, or ML will help you to predict better, but basically analytics, the intro exploratory data analysis helps you to understand better. We always say that from an engineering and life science perspective, understand the data, understand the process, understand the phenomena, understand the variations in the process, and then you can find out techniques to reduce it. So that's where you start exploring the data. You want to fit distribution. You can check which distribution fits better. Okay, whether it's a Gaussian, Weibull distribution. Understand the data from distribution perspective, because that's what help you to build robust processes when you're deploying at an AI using AI scale. Because anything you do at a lab level is all fine, engineering perspective, but you want to scale it up your manufacturing process, then you have to add a little more how many? Okay, there was one question. It's good. How many variables we can have and how much minimum data sets are required? That's a good question. We'll come back to that. It depends on what's your problem. Okay. We always say more data doesn't mean more accuracy. Very important. Okay. This is my personal experience. More data doesn't mean more accuracy. More data means more confidence in your results. Very important. If the data itself is wrong, the quantity doesn't make any sense. Okay, you look at the quality of the data and as well as quantity of the data. Quantity is important. We always say thumb rule of for every one variable, you should have at least 10 records. Okay, 10 observation. If I have 30 variables, columns, then I should have 300 variables minimum. Okay, at the same time to have enough degrees of freedom to fit a statistical model or a machine learning model. At the same time, not every time you'll have data. You might have to bootstrap or else so-called simulate the data or use synthetic data. But classically speaking, from an analytic statistics standpoint, more data is desired. At the same time, more of good data is desired. Okay, more data doesn't mean more accuracy. Okay. Okay, let's do this. First, fit a predictive modeling. Somebody is asking me question. Okay, repeated optimum conditions are there. We will come to that when we do the optimization. Okay, so I might do a lot of visualization here, and then I'll try to fit a regression model here. Okay, I'll put a simple regression model. Yield is my Y variable. I will take all this variable and I choose whatever regression technique, simple regression technique I will choose, and I'll see that I'll fit a model here. Okay, this is my regression equation. You can see y is equal to mx plus c kind of regression equation. And you can see that lot many variables are, I get an R square of 0.71. Okay, I'm putting a simple regression model. Not all the variables are statistically significant here. And I'll start building a parsimonious model. Okay, I'll start removing variables which doesn't contribute statistically. Okay, are not so significant. And I build a parsimonious model. Okay, so I'll remove automatically my regression gets the coefficient gets adjusted or populated. Okay. Okay, this is my parsimonious model. Even compressor is not making sense. Oh yeah. So now look at this. I built a model with where R square is around 0.65, simple statistical model, where the variables which are affecting the top variables which are affecting my yield are agitation, temperature, pressure, time modifier. Okay. A simple linear model I've built. I can also build, given this context, I can build little more, let's see, what are the variables. Okay, agitation. Okay, agitation is categorical, that's absolutely fine. Temperature, let's say agitation, time, temperature, pressure. Okay, and modifier, where is modifier? Okay, then I can build a little more non-linear model. Okay, I'll put a response surface, little more non-linear quadratic model. Let's see, let me see if my R square increases. R square is 0.65. Let me commit. Oh, not bad, look at this. If I build a nonlinear model, the R square increases to 0.8. Not bad. That means there is a nonlinearity I can see. Now that you need to understand, this is your regression model. Okay, a little more quadratic model. I can see that visually. This is what I spoke about, understanding your analytical or a machine learning model. And there is a tool within JUMP called Prediction Profiler, which can help you to understand better. Okay. Now somebody asked a question, how can we minimize error? We'll come to that. Okay. So yield is on the y-axis. This is what we are looking at. And the modifier is on this modifier, temperature, agitation, time, and pressure. Now look at this. Keeping all other variables, if I increase time, look at this, my yield increases, but after some time, yield decreases. This is what I'm talking about, non-linearity. Okay. So I'm trying to understand in machine learning, you might not get this kind of level of understanding always. Again, always in some algorithms you will get it, but not always. Sometimes it works as a black box. Now you see at lower levels of time, my modifier doesn't have any impact on the yield. If I increase my time, look at this, modifier has a positive impact. At the same time, lower modifier as a inverse relationship. If I increase the modifier, look at this. This is so trying to understand how variables interact with each other. At the same time, what will be the impact on the yield variable? This kind of visual understanding is important in engineering sciences before you build any kind of predictive modeling. I realize now with a simple model, there is a non-linearity, there is an interaction effect. I can also see that using here, let's say, let me see interaction profiler. I can see it, you can see that. Or there are a lot of interaction between variables, two-factor interactions. I can also test three-factor interaction. I didn't do that, only two-factor interaction, I did that. So now, next question is, instead of simple analytical model like this, I didn't apply any kind of chemometric or a multivariate techniques here, just from a perspective. I can also apply a little more machine learning algorithm. Okay, ML algorithm. There are a lot of popular machine learning algorithm. For example, you see predictive modeling. When you build a predictive modeling for ML, I split the data into, let's say, 75 and 25. Okay, I create a column just to have a honest assessment of my model. And whenever you build a predictive modeling, machine learning models, you split the data, you create the model on the training data, and then test the performance of the model on the validation. That means you create 75, 25, 70, 30, 50, 50, 60, 40, depends. Okay. So now I split the data into 75 and 25 quickly. And then let me apply a neural network. Okay. So now yield is my Y variable. I know only these variable affects. Okay. And this is my validation column. And I'll try to deploy a model. A little more activation functions. I can build a simple neural network model quickly. Now, the neural network model is giving me R square of 0.6, which is less than the regular analytical model. But I can fine tune this model, not an issue. Now, as a researcher, you can apply any kind of machine learning algorithms here, a partition algorithm, whichever algorithm. Now you see under analyze predictive modeling, lot many ML algorithms are there. But if you're a researcher or a problem solver, if you don't have time to go through each of the algorithms and then decide, there is an option called model screening in JUMP, where instead of me applying the models and then checking which model works better, I will ask JUMP to run all the models, add two-factor interactions and quadratics, and then let it build all the models and then tell me which is a better model. Kind of auto ML. This is where you're getting to the AI component. Okay, minimizing the human intervention. Look at this, click of a button. I created all these models. Okay, this is my training. Okay, this is my validation. Looks like neural boosted has performed really well. Okay, given this context, I can run selected and then I can start looking at this is my
Sir,
neural network model.
I have one question.
Go ahead, sir.
This neural network of modeling tells the predictability depending upon the R square value.
Mm-hmm.
Uh, if the R square value is above 0.95, that can be a best model or algorithm. Is it so?
No, there are two components. Very good question. R square getting 0.95 is possible in engineering sciences, but that is not desirable always. Okay, not every time
Yes,
you'll
yes,
get a
I agree.
0.95. Okay,
Yes.
sometimes that's called overfit model. That means you're modeling for not the average, including the noise you are modeling it. My objective of building any predictive modeling, it should give me the average effect and it should work in all situations. Overfit models, R square 0.95 is desirable, but in most of the life science cases, if I'm getting 0.95, I start doubting the data because there could be some manipulation about the data. Not every time you'll get 0.95. Just to give you context, you know, the life-saving drug, Covishield, what is the efficacy? Will you get 95%? Was that 95% efficacy? No, right? No. So I always say that statistical significance versus practical significance is important. You look at statistical significance 0.95. No, practical significance is most important. So now coming from south of India, we have a say. So my mother keeps telling me, eatable idli is always better than a fancy pizza. Okay, you understand idli
Right.
versus pizza. Yeah. So consumable, look at deployable. So most of the models statistically accurate, good, efficient model, but if it is not usable, probably I stay away from it. Even a medium performance, mediocre, deployable model is always good for humanity and engineering sciences than a statistically good model which is not deployable. You got my point? Okay.
Yes, yes, yes,
Desirable is most important, but you need to think from a context perspective.
yes.
But I hardly see a 95%, 99%, and I start doubting the model. Okay. So
That
it
means
should be
R
highly
square value should
calculated.
be above 0.7
No, again, it depends on context to context. Now I'll give you a life science case, even if it is a 0.4, 40% predictability for a breast cancer case study, life science case study. We will take that. We don't wait for 0.7%, 70% efficient model. Even 40%, if you're ready to predict a person has a cancer or not, that's a good model sometimes. From a civil engineering perspective, if I can predict there could be a earthquake or a catastrophe to an extent of 30-35%, that's a good model. You don't need 90% efficient models, and you cannot build because you'll not have data most of the times. You have to synthetically create a data and then build a model. So in that case, look for a practical significance versus statistical accuracy. There is always a debate over that, but always practical significance will. Good to go?
Yeah, thank you, sir.
Okay. So now that I think that neural boosted has performed, good question, great questions. Run selected, I'll build this model. Okay. Now that this is my final model I have chosen, assume that it has given me 69%, 70% efficiency, not bad. Okay. From an engineering perspective, predictability to 70% is actually good. Take it from me. Now, if you want to next level is little more optimization. Okay. Now that you see a lot of non-linearity here, okay, now you can see this is the most prediction profiler I can see. Now that somebody asked me a question, what should be you want to get to the next level of optimization, I can run a gradient descent algorithm, and then I want to maximize my yield, I can use the optimization, maximize, and remember. Now it runs the optimization gradient descent algorithm in this case, and then says, Murli, keep the modifier at 110, temperature at 388.40, agitation low, and then time at this, pressure at 17.61, you'll get a yield of 79. Okay, with the confidence band also you can get. That means I'll be achieving 88% desirability, not bad. You're achieving decision making to an extent of 88%. And our requirement was at least cutoff was 70, 75. You will achieve 79%. Now look at this. The problem we had was that we also explored the data. We built multiple predictive models, and then we optimize the process also. Now that we want to deploy this model, okay. Now that I've created this, I have to create an automated system so that from an AI perspective, I might be using, let me build this, and I can publish a prediction formula, and then for my system, front-end system, I can generate a Python code if my front-end environment is Python, or else a Java code, so that I'm covering from data to decision. I explored, I applied analytics, I applied machine learning algorithms. Now that I'm deploying the code also, so a complete AI solution is built into the manufacturing process, so that my yield will be at least 74, greater than 75 in this case, assuming that there'll be some standard error or variation in the process. I would have also gone one step ahead. Okay, I would have also gone one step ahead by doing little more Monte Carlo simulation here. Okay, to see synthetically generate the data from an AI perspective. So I can show you that also by introducing little more variations in my process, and then see, let me add a little more noise to my output also, and then I can start simulating the data. This is my synthetic data. Look at this. I've created around 10,000 rows of synthetic data so that I can understand the distribution here. Okay, while building the solution. So when you look at the robustness of process, that's where you want to accommodate for the random variations in the process also, so that the Monte Carlo simulation will help you to build robust processes in manufacturing and operations anywhere you're looking at. Okay, so this is how kind of I just wanted to show how a problem can be solved by applying machine learning algorithms. Either you explore through proper understanding of the model and the data, exploration of the data, and the different models. You have to fine tune. I didn't show you a lot of fine tuning model. For example, in this case, if somebody is exploring neural network or XGBoost for that matter, okay, somebody wants to explore extreme gradient boosting, and you can also fine tune your hyper tuning parameters. Okay, gradient boosting algorithm. Okay, you can select any kind of your activation functions, the gradient boosting, those kind of things. You can jump as also a little more on the torch. Okay, PyTorch deep learning. You can apply those algorithms to fit a better model in terms of accuracy. Let me try, now that I've been talking about a little more deep learning AI solution. For the same data, let me try deep learning also. Okay, torch deep learning. I'll take this yield here. Let me say these variables to X factor, and I'll take validation. I would have shown a little different example. Okay, we can see that you have all these activation functions, multi-layer perceptron, radial basis, mixed model you can build. Let me directly build. Okay, let me do a deep learning algorithms quickly. Or not, it's not working. Okay, probably I have to fine tune my algorithms here. Not a better model. Probably I'll use the regression model only here. Okay, it's an overfit model. You can see that from yield perspective. Now, again, as I mentioned in the beginning, it's not about the algorithm, it's always about the problem solving. Now you can see that lot many algorithms are there, which gives you better deployable model. Okay, sometimes neural networks may not be explainable. I think some of you might work in a regulatory environment from a FDA perspective, or else any kind of regulations, where if you build a black box system, probably they may not accept it. You might have to use a model, an AI system, or an ML algorithm, which you can explain better and document better. Not all the models are explainable, especially in life sciences. FDA wants to understand before implementing any of the solution, because the risk levels are really high there. Okay, given that context, try exploring multiple algorithms as well. Okay, so I'll show you one more example. Okay, if you have any questions. Okay. Any questions?
How come all models are not explainable?
Oh, no, who said that? Simple model is explainable. You know, I showed you this model is explainable. Okay. Simple regression model. Now this is explainable. I can easily see. Okay. And then when the modifier increases, yield increases. But temperature, so you can see that temperature has an inverse relationship. It is a non-linearity. Okay. So some models are good for prediction. Some models are good for explanation. Some algorithms. That's the reason there are plethora of algorithms available. And based on your need, your requirement, you use that algorithm. Again, some of them might give you statistically good results. Some of them might not give you statistically good results, but they might be useful. You got the point?
Yes, yes, sir.
Okay. How to compute synthetic data? Oh, very good question. Okay. Synthetic data approaches, now that there is a generative AI, but generative AI might have a backend large language models, but from a process data, if company has, the only way to create a synthetic data is through understanding the distribution of that variable and then applying Monte Carlo simulation, keeping that distribution in mind, and then adding little more noise or standard deviation into your existing process variables, and then create the synthetic data. One example I just showed you, right? In this case, if I look at this, I can use the simulator. Okay, this is what I'm talking about. Simulator, where I can simulate the data. I can see, I can, instead of fixing it and make it as random, this is also random. Let me fix the agitation and then random. This is random. If I know the distribution of the variable, look at this. I know this might be log normal, this might be exponential. If I know the distribution really well, I can just let me put variable, okay, variable distribution. I'm just showing you some of them. Then you can start simulate the data to around 50,000 rows. Okay. Now that I can simulate the data table, making it. Now you see 1,000 rows I simulated. There's a lot of noise in the background. Can somebody unmute? Somebody mute the other participant. Yeah, thank you so much. Did I answer your question? One way is to simulate the data using a distribution profiler like this, the way I showed you now. Does it make sense, sir? Okay. It's more of, yeah, thank you so much, Srinivas. Thank you. Thank you, Professor. Okay, so I'll show you one more example for quick 1 or 2 minutes, one through on a image data. So most of chemical engineers will have a lot of data sets with image. This is a synthetic data. We call it as, so it's kind of civil engineering, material science engineering, you can think about it. Okay, so just to give you a little more fun example here. Okay, so I'm showing, let me close this. I'm not going to save anything here. Now I'm going to use a data called, so NASA has just delivered samples from Mars. Okay, this is a Mars so-called spectrometry. Okay, spectrometry data. So let me open the data set. It's there here. Okay, Mars spectrometry data. You will read. Let me close all this output first. Okay, a couple of seconds. No. Untitled. Okay, Mars spectrometry. I have a lot of image data. I thought of let me take that data. Mars spectrometry data I have here. Okay, so let me open the data set. Deep learning. Okay, Mars spectrometry data I have here. So now we are looking at, there's an image. I've already loaded the picture here. Okay, we are trying to determine the chemical composition with mass spectrometry. That's the preferred approach, right? So the composition of unknowns can be difficult to determine and quantify precisely. Okay, so normally we convert the mass spectra into spectrogram images using Python or any kind of software, and then use modern convolutional neural nets to predict the composition. Now this is my image here. Okay, this is my image. I've loaded the image data, and I'm trying to model iron oxide here, whether it's present or not based on the image I want to predict. Okay, that's the and then I want to use kind of a split that into two groups, 1 and 0s. I can build a simple model, but little more deep learning model. I wanted to show machine learning model. I'll go towards deep learning, and my image picture is my factor. Okay, and let me put iron oxide. Okay, iron oxide is my response, and then I'm trying to use split validation. Okay, so now let it be. You can also fine tune it. Okay, activation functions is a small data set. Let me run it. Okay, let me run the deep learning ML algorithm. It takes some time. I can fine tune activation functions, your epochs and learning rate, all those things. Yeah. Not bad. Oh, yeah. So not bad. So training accuracy is 7.78 and validation accuracy is 0.78. Okay. So now this is how quickly I can deploy the model, and then I can see a little more. I can save it as predicted values, and then save model, I can deploy it. Just quickly, I wanted to show this. That's the reason. And then you can also see decision threshold by default. Any classification model, we keep it as 0.5. But what if there is a change in your decision threshold? What will be the impact on your specificity, sensitivity, those kind of exploration also you can do with just a click of a button. So you might be using any other tools for that matter. But,
Dr. Murali,
yes.
just a reminder for about the time. Time is
Yeah,
7:47.
I'm done. Yeah, I'm done. I just want to summarize now that most of you are researchers and professors here, and you can be tool agnostic. Okay, that means technology agnostic, and then problem centric. That's what you teach as well. And just to give you a context, this software, GEM software, which I showed you, is extensively used across industries. You can see chemical. If you look at this chemical industries, I feel all the 10 of the world largest chemical companies use GEM. When I say it's industry driven software, and the best part is we are giving you this software completely free for teaching and academic research. Feel free to connect with me and explore this software for both teaching and academic research and solve problems. Okay, so I'll stop at this point of time. Thanks for your time, and I'll open for the Q&A for next 10 minutes. Stop sharing.
Sir, my question is, if you have, let's suppose if I have image, that might be the data of some samples, by which I have its other distinct features also. Let's suppose I used XPS for that, where I get other things also, like the elemental composition as well.
Agree with you.
Now my two questions here are, one thing is, what should be my axis, number one, X and Y. And second thing is, if I can get the composition that is in with regard to what I will get the composition. In other words, whether properly we can predict what is the composition of the material, because if that we can do, that is great.
Okay, so for that, now you have a multiple responses here. Okay, so first thing is, the way I look at from an analytics standpoint, your Y has many variables. Okay, and your X is only image. Am I right? Yes or no? Okay. Yes. So then you have to build a multiple response optimization model using deep learning, and then you can predict. So given the image, what are the probabilities or what are the propensities of each of this component, the presence of possibilities of presence. So either you can deploy it individually models, or else you can deploy multi-response models also, and then choose. And then based on whichever is the highest, you might get composition. Definitely it can predict, given this image, what will be the composition, you can predict. That's where you can use machine learning, deep learning algorithms. Yeah, given this image, what are the, so if you have training data, definitely you should have training data. Okay, provided you have a very good training data and you have built a model, and then unknown data will definitely perform well. Normally in this case, I would say any kinds of deep learning, machine learning algorithm you're building, use a k-fold validation is preferred. Okay, instead of splitting into two, it's always preferred for deep learning k-fold validation, and make 3 folds or 5 folds, and then repeatedly run the algorithm for better accuracy. I would say it is possible. You can apply these kind of techniques. Yeah.
So what if instead of going for deep learning, I do one through XPS, one through Raman spectroscopy, and one more to other something, and figure out what is the composition through this image modeling to some extent, or simulation, and later figure out based upon justification the composition of the material. Is it fair enough?
So I probably need to do a little more library on that for that question. From a data perspective, that's what I gave my thought. What should be the approaches? I would think this is just shooting in dark. Is you try to do all those. And also there is another one called ensemble techniques. We use that word. Instead of one single approach, you can use multiple approach to solve the problem. And one approach could be this way is what I would think.
Okay, thank you.
It's kind of intelligence of mass, average mass intelligence. Instead of restricting to one approach, let's have multiple approach and see what gives me the best, or else take the average of it. That's also one approach. Again, this is shooting in dark. I might have to do library given this context.
Okay, thank you, sir.
Any other questions? So just for others who wants to use the software in your classroom or as for research, and this is where I want you to remind gem.com/student. Okay, anybody can go ahead and then use their college email address and then download a fully functional. If you're doing chemometrics or multivariate data visualization, reliability, quality, Six Sigma, whatever predictive modeling, all those things you can go ahead and then download and then use the software. And it's an industry-driven software. Used across institutions and as well as commercial clients. Yeah.
Participants, do you have any questions? Any more questions?
Looks like I'm giving you 7 minutes back as a bio break.
Okay.
I thought I'll have questions, so I curtailed my presentation. Yeah. I would have taken one, two more examples. Yeah, that's fine. I think if they got the focus and then the thought process behind that, should be fine.
Yeah. I just want to add the participants are not only related to chemical engineering as such, they are generic.
Okay. So,
very
yeah.
generic.
Again,
okay.
the problem remains problem for me. We always, any software will treat Y as a Y, X as a X. So they don't understand what is your chemical.
For you look at the numbers, right? You look at the numbers.
I just took the example.
Yeah.
So I would have taken this. There are a lot many examples I have. Okay, so if you look at it, yeah. I didn't realize that.
No,
okay,
I would like to just say that, I mean, you highlighted the application in chemical industry. I just want to know that even semiconductor industries and other process industries also utilize that. And that would I like to stress here.
Absolutely. I see, if you look at the industry perspective, I'm just not sharing the screen now. So semiconductor is extensively, and just to give you the context, we see this. When I look at the industries, pharmaceutical, chemical, semiconductor.
Consumer products,
the top semiconductor industry. Just to give you all 25 words, top semiconductor use Java. In that way, they might be using design of experiment, material science, predictive modeling, quality, Six Sigma, all those things. From an R&D perspective, reliability studies, yield, quality. So they might use this. Yeah. I had some semicon cases also. I didn't realize that there are a lot of semicon people here. Yeah.
Okay. Good. If there are no more questions.
Okay.
Okay. Thanks, Muralidhara.
Okay, somebody said ML is less accurate to deep learning for large sets of data based on network. Now again,
question is there.
There's a subjective approach. Now ML, it depends on how do you tune your model. The second thing is how much complex data set you have and how clean your data set is. Again, focus on the practical significance, not on the statistical accuracy. This is my humble request for all the people who are doing data analysis. Look for deployable, easy to understand, easy to deployable models rather than a complex, unexplainable, accurate model which may perform statistically well on the given data set, but practically, if it is not making sense, I rather stay away from it. Yeah, I always stay away from statistical accuracy. I give equal importance to statistical accuracy and practical significance. Okay, we'll look for translation research and how a model can be used is most important than what is the accuracy of the model. Yeah, if it is usable only, then I look at accuracy of the model. Sometimes I might compromise with the accuracy if it is usable. If it is not usable, then even if I build a 100% accurate model, if it is not usable, probably that's not a good idea long term. Absolutely right, sir. Okay.
Okay, that's good.
Any questions? Okay. If not,
Okay.
I'll stop sharing it. Okay.
Okay. So I take this opportunity to thank Dr. Muralidhara for the session 1, for inaugurating the session. So you are the first one. So you have given a better clarity about AI, data science and ML, and better clarity about how to analytics. In other words, how you deal with analytics as such. So it was indeed a great session. So your feedbacks are coming in. Okay. Rajesh, can you share the feedback
Feedback,
link?
right?
Yeah,
Yes,
feedback
yes, I'll
link.
share.
Yeah.
Thank you,
The
sir.
yeah.
Thank you so
Have a
much. I think
Yeah.
I will definitely, I look forward to connect with you
Yeah.
in whatever capacity. And thank you so much for giving me this opportunity. It
Yeah.
was
I
great.
will share the feedback also, Doctor.
Sure,
Yeah.
sure,
Okay. Once the
Okay.
participants provide the feedback, I will share the feedback to you also. Yeah.
sure.
It will be there.
Okay.
Yeah. So participants kindly uh, provide the feedback, and we'll give you some few questions also, just to on the topics whatever he has covered. Some 5 MCQs just to repeat it. So it will be useful for you. Okay. So please try to go through that questionnaire also for this session. So for each session, we'll be providing you the Google form to fill the feedback, as well as a small questionnaire, so that you can train on the materials what he has provided. Okay. Thanks, sir.
Thank you so much, sir. With
Thank
your permission, I'll leave this session.
Yeah, thanks. Yeah, we'll get back to you, Muralidhara, later. Okay. Tomorrow morning, we'll get back to you.
Thank you. Have a good day, sir.
Yeah.
Have a good
Have
day.
a good day.
Good
Have a
day.
good
Thank
day.
you so much for your time. Have a great rest of the day and continued session. Yeah.
Thank you. So, Rajesh, can you share the Okay. We'll have few minutes left
Sir, you have
for the
muted.
next session. Yeah.
Rajesh sir,